silent for 37 years, then NASA fired them up. This is the story of 4 dead thrusters on a spacecraft 21 billion kilometers from home, and the engineers who had to bring them back to life without ever touching them. If you want more real, unresolved stories from the edge of what we understand, subscribe and stay through this one. This is Deep Space Anomalies. 21 billion kilometers away, a machine built in the 1970s is about to get a wake-up call. November 28, 2017. Engineers at NASA's Jet Propulsion Laboratory send a command to 4 thrusters that have not fired since 1980. No one on Earth knows if they still work. 19 hours and 35 minutes pass before an answer arrives. The people who built these thrusters are gone. The team waiting for a response never touched the original hardware. Nobody has tested this in 37 years. They are about to find out if it still runs. Voyager, one talks to Earth through exactly one channel. A 3.7 meter dish antenna, aimed with almost no room for error, carrying a signal across a distance so vast that light itself takes over 19 hours to cross it. Small thrusters keep that antenna pointed. They fire in brief, controlled pulses, nudging the spacecraft back into alignment whenever it drifts. But since 2014, something has changed. The thrusters need more pulses to do the same job they used to do with fewer. Degradation, slow and steady, the kind you cannot reverse. More firings mean faster wear, and wear out here is not a problem you can fix with a replacement part. There is no next shipment of propellant. What is on board is what will ever be on board. The team at JPL is watching a resource running down in real time on a spacecraft that left Earth in 1977. And here is where it gets strange. The fix they are considering is not a new part. It is an old one that has been sitting completely unused since before most of the engineers in the room were born. Voyager was built with a second set of 4 thrusters. A backup, in a sense, though calling it that undersells how differently it was meant to be used. These thrusters last fired on November 8, 1980. Their job was never fine pointing control. They were built for trajectory correction, the kind of adjustments needed during the flybys of Jupiter and Saturn, big deliberate burns to change course and aim instruments at a passing world, fine attitude control. The millisecond pulses needed to hold a dish steady on Earth is a different task entirely. This branch has never once been asked to do it. So the question is not simply, does this hardware still work? It is, will hardware designed for one job behave predictably when asked to do a completely different one, after sitting untouched for 37 years at a distance where there is no way to check in the middle? To answer that question, JPL does not turn to new technology. It turns to memory. Propulsion specialists Chris Jones, Robert Shotwell, Carl Guernsey, and Todd Barber are brought in to reconstruct exactly how this dormant branch should respond. They dig through decades-old records. They examine software written in an outdated assembler language, a language from an era most current engineers never trained in. The thrusters themselves are not simple machines to reason about after decades of silence. These are MR-103 hydrazine thrusters built by Aerojet Rocketdyne. Liquid hydrazine passes over a catalyst bed and decomposes into hot gas, producing thrust with no spark, no ignition system, nothing that behaves like a conventional engine. That chemistry is precise, but it depends on components that have never been tested after this much time doing nothing. Valves could have degraded in ways nobody can observe from Earth. Propellant pathways could have shifted. Heaters have to keep every part of the system inside a narrow temperature band, and if any one of them has failed silently over 37 years, the team will not know until the command is already gone. There is no simulator that can fully replace that uncertainty, so they model what they can, weigh the risk, and prepare a single sequence of commands they believe is safe. There is no room for trial and error here. At 21 billion kilometers, there is no live control, no joystick, no way to watch the first pulse and adjust mid-sequence. The complete command has to be judged safe before it ever leaves Earth, because once it is sent, there is no calling it back and no correcting course halfway. They send it complete. The command leaves Earth and travels for hours before it even reaches the spacecraft, crossing a distance so large that the delay itself becomes part of the experiment. Then, aboard Voyager, the actual event happens. 4 thrusters fire. 10 millisecond pulses each, precisely timed, exactly as the models predicted, or exactly as they failed to predict. Nobody watching yet knows which. On Earth, nobody knows this yet. The result of that firing will not reach a deep space network antenna in California until nearly 20 hours after it already happened. For almost a full day, the outcome already exists somewhere out past the heliopause, fixed and unchangeable, while the team that sent the command can do nothing but wait. There is no partial signal, no early warning if something went wrong. Just silence, then eventually data. The kind of wait where every hour adds to the tension, because there is truly nothing left to do but let the physics finish crossing the gap. Then the telemetry arrives. All 4 thrusters performed exactly as intended. Hardware built in the 1970s, dormant since 1980, has just accepted an entirely new assignment after 37 years of silence, and it did not hesitate. The 2017 firing did not succeed because 1970s machinery somehow escaped 37 years of aging in the vacuum of space. It succeeded because the original spacecraft was built with real redundancy, and because a later generation of engineers was willing to reconstruct from old records and outdated code exactly what that redundancy could still safely do. Voyager crossed the heliopause years ago, but it also crossed something else, a generational boundary. The people who designed it are gone. The people commanding it today never touched the hardware. And yet it still listens, it still responds. Because somewhere between 1977 and now, the knowledge of how to speak to it got handed forward, one team to the next, so that a machine older than most of its own operators could still be told what to do and still obey. If a story like this is the kind of thing you want more of, real, documented, and stranger than fiction, subscribe to Deep Space Anomalies. New episodes cover the unresolved signals, the machines that outlive their makers, and the mysteries still sitting at the edge of what we actually know.